welcome back. In this lesson, we're going to finally apply some of those statistical rules and confidence intervals into a topic known as hypothesis testing. All right, so it's kind of a formalized procedure for basically putting statistics to work for you to measure something or to make a prediction about what a population is doing, or in the case of quality assurance programs, when should maintenance on a piece of equipment be maintained. It's a really kind of a fascinating area to study, and on the first pass it can be a bit overwhelming, but I'm going to kind of break this down into some pieces, and hopefully it will make sense as we start to move through this. So without further ado, here we go. All right, so basically hypothesis testing involves literally doing a test, and by a test we mean that we're working on that we take a sample or a measurement or something to gather some data, okay? And there are several elements that are required in order to be able to set up a statistical test. Okay, the first item is what we call the null hypothesis, okay? And often this is called as H0, okay? And it's some statistic or statement you can make about one or more of the population parameters, okay? And so maybe we're looking at the, average, number of people in our restaurant at any given time, And so we could set a statistic of, our hypothesis is that there's, 10 in the restaurant at any given time, and so now what we'll do is we'll set up an experiment in which we can go through and either prove or disprove that fact based off of sample data or samples, okay? The second criteria then is we come up with the alternative hypothesis. Okay, often this is called HA, though I have seen this called as H1 sometimes, but HA is how I learned it. Okay, and so this is the alternative to the null hypothesis. And what that is this is the hypothesis that we should accept if the null hypothesis is rejected. So you can almost kind of think of this as being like an H0 complement kind of thing, right? If I don't have this one, then I got to have this one. I can't have both. Okay, so that's kind of what we mean. Like I say, we won't get too bogged down in the semantics of the wording of this at this point, but just kind of an awareness is all we're looking for. Okay, the third item is that we need a test statistic. Okay, and this is some parameter from the test data that we will try to use to prove or disprove, not disprove, but reject the null hypothesis. Okay, so in the case of our example where we're looking for the population average on H0, then a good test statistic might be the sample average or the sample mean. Okay, now this gets into a lot of our point estimation and how do we choose these. So again, we'll save a lot of the subtle nuances of how do you choose this test statistic for later. I'm interested more in kind of illustrating the mechanics of what it is that we're trying to do. All right, so that's our test statistic. Okay, and then the last term is what we call the rejection region, or sometimes known as the critical region. Okay, and this basically identifies the values of the test statistic that will imply rejection of the null hypothesis. Okay, so like I say, there's a lot of words going on here, and so all we're really doing in a kind of a fancy way is we're basically setting up a confidence interval. Okay, now there is some more to it before we can actually dive into that, so I'm going to proceed through that, but that's kind of where we're headed with this. So we're going to keep our eyes open on all of these, and I'll outline a method later that will formalize a lot of this, but those are the main highlights of what we're trying to do. Okay, now what we want to do in a statistical test is we need to be able to evaluate several properties, okay, and it revolves around a 2x2 grid. Okay, what we have is a couple of different events. On this axis I have the decision of my test. Okay, should I reject H0 or should I accept H0? This is probably better off written as do not reject, because as you'll see, accepting something does not imply that you're rejecting it and vice versa. Okay, the true on the horizontal axis then is what reality is, or what we call the true state. All right, and so we have the true state that H0 is true, or the state that HA is true. Okay, and so what happens is some interesting things can kind of occur here. For example, if the true state H0 is true, and I choose to accept H0, then I made the correct decision. And likewise, if the true state of HA is correct, okay, and I choose to reject H naught, then I made the right decision, okay? Where the interesting thing happens is, what happens in these other areas? What if H naught is true, but my statistic tells me to reject H naught? Okay, well, this is what we call as a type 1 error, okay? And the probability of a type 1 error, okay, if I slide this up a little bit, is commonly denoted by a value alpha, okay? And then if we look at the last one, the type 2 error then is the alternate hypothesis, HA, is true, but we choose to accept H naught in general. Now, a lot of times we tend to focus on type 1s, but there are occasions where type 2 can be relevant, depending on how we set up the problem or set up the parameters of the study. Okay, now for a type 2 error, the probability of a type 2 error is often denoted by beta. And what happens is as I increase alpha, the beta tends to go down. So as I change the confidence interval level and increase it, then beta in return will start to decrease. So the confidence in the second guy will start to decrease. All right, there's kind of this play on it. And so there's some unique values that exist for alphas and betas. For example, alpha is usually set as, 1% or a 5% or a 10% seem to be the most common. Right, but if I chose a 50% on this, and I would get something in beta that's a mid-range value, it would be hard to tell the difference between a type 1 error or a type 2 error. I wouldn't really be able to make a decision. So there's kind of an art to how you start to choose these values. But for us, we're going to focus mainly on these three, and more specifically, all our examples will work with the 5%. Okay, so that's kind of the basics of where we're going with this. All right, so let's give kind of a test, a setup of an example to kind of explain these errors to you. All right, so what I've got here is an example that involves two bowls of marbles. Okay, the bowls are identical. They look exactly the same. There's no distinguishing characteristics. Bowl 1 contains 60 red marbles and 40 blue, and bowl 2 contains 40 red and 60 blue. Okay, so we can compute the proportion of red in bowl 1 as being 0.6. That's 60 over 100, 0.6, 60%. Okay, in bowl 2, the proportion of red then is 40% or 0.4, and we're going to call those as our proportions, this little script P thing. Okay, now, we walk into the room and one bowl is sitting on a table, but we don't know which one. Okay, we can't see inside, I can't count the marbles. Okay, what we're going to do is we're going to draw a sample of 5 marbles out of this. Okay, we suspect it's bowl 2, but we can't be sure. Okay, so the sample statistic that we would use on this then would be the number of red marbles, okay, that we pull on our case of 5. Okay, so what we look at then is setting a null hypothesis that the probability of drawing a red marble is 0.4. Okay, and this was the bowl 2 proportion. Okay, we're going to define a random variable x as being the number of red marbles that are drawn. Okay, and then the null hypothesis is going to be rejected with the occurrence of 5 red marbles. Okay, and that's going to be our criteria for rejecting this. Okay, now again, we didn't specify an alpha value or anything, but we can kind of start to show how we can back our way into this. Okay, so 5 red marbles is what we're looking to see drawing out of 5 marbles placed or pulled in the sample. Okay, so this is basically a binomial situation. Okay, so my alpha parameter for the type 1 error, the probability of a type 1 error then is the probability that x is equal to 5 when my proportion is 0.4. And again, the 0.4 came out of the bowl 2 criteria. Okay, and if we write this, because we know that it's binomial 5 and 5 and 0.4, and you can solve this binomial. I'll show you the equation down below a little later. If you don't remember how to do the binomial, we've got a video on that, so go back and take a look on that, and then we'll explain in great detail how that one is set up. Okay, but for now, I'm going to assume that we know all of that since we're a little bit later on in the course now. Okay, so using our binomial, which is basically a red or not red case. Remember, binomial required one of 2 possible outcomes. Okay, I'm going to do 5 tests. I'm going to pull, and I'm looking for 5 successes at a rate of 0.4 raised to the 5th power, the number of successes, multiplied by 0.6, which is the complement of this guy raised to whatever else is left. And so in this case, I'm looking for none of those. All right, and when I do this, this means that our alpha has a probability of 0.01024. Okay, so the probability of incorrectly rejecting a null hypothesis on this particular problem would be a little bit more than 1 in 100 chance, a 1% chance. Okay, now it doesn't mean that it can't occur, but that's how we define that. Similarly, for the same problem, we're going to define beta as being the probability of a type 2 error, okay? And for that, then, it's basically, we're looking for the case where, the probability of x less than or equal to 4 when the proportional limit is 0.6, okay? And so we can go through and we can kind of do a complement calculation on this. Okay, so this was the probability of x being equal to 5, okay, when proportion is equal to 0.6. Okay, and I can subtract that off of that, and that will get me that same quantity. Okay, so when I do that, it's 1 minus, we just plug into the binomial, 5 on 5. Now my success is 0.6 raised to the 5th power and 0.4 to the 0. I get a probability of about 92.24%. Now, you'll notice that if I add beta to alpha, I do not get 1.0. Okay, there's always a region of uncertainty that we're not sure which one is happening. Okay, so that's one of the dilemmas in hypothesis testing that we'll have to face. But that's kind of how we start to kind of get a sense of alphas and betas. Now, for most examples, again, we pull historical data and we arbitrarily set alpha. Okay, but depending on how you set your criteria, you can choose alpha whatever you want. We just chose to define the rejecting the hypothesis. If I pulled 5 marbles, out of them and they were all red, okay, and that would help us to hopefully deduce which bowl that we're looking at in this. So again, I know it's a little abstract, but hopefully just kind of getting you kind of a feel for the taste of what it is that we're trying to do. All right, now, before we go any further, let's set up a procedure for hypothesis testing. All right, okay, and so it's basically 5 simple steps. Well, maybe not so simple, but it's not too bad. And I'll walk you through an example here after we get this outlined. Okay, that we're going to specify our null hypothesis and our alternate hypothesis in an acceptable level of alpha. So again, 1%, 5%, 10%, or you compute it like we did in the last example, whatever you want to do. Like I say, typically 5% seems to be the most common. We're then going to, our step 2 then is we're going to define a sample-based statistic and the rejection region for the specified null hypothesis. Okay, step 3, we're going to collect sample data and calculate the test statistic. Okay, and then step 4, we're going to make a decision to either reject or fail to reject H0. Now, the wording on this is really important on this because I can either reject the null hypothesis, okay, or I fail to reject. It doesn't mean reject and accept. Failing to reject H0 does not mean accept it. Okay, it just means that your test did not, explicitly rule out H0 as being a possibility. Okay, and so that's a little bit of one of the subtle nuances of what it is that we're trying to do here. And then the last step is obviously interpret your results. Generally, this is some call to action. In a quality assurance program, maybe it means you go fix the machine that's broken, okay, because now it's not producing like you expect it to based off of your testing data. All right, so let's try one. Okay. It's a little wordy, but hopefully it makes some sense, okay. We have a company that's going to package 8 ounces of snack packs. Okay, it could be peanuts, almonds, trail mix, whatever, but they're wanting to package 8 ounces at a time. Okay, and they want to maintain control on the amount of peanuts or snacks. I say peanuts, should be snacks. Okay, that are put in a package by a specific machine. Okay, now, the way that control is defined by the company is that we're going to average 8-ounce packs. Okay, and that we are not consistently over or under filling, okay, with a minimum of 7.9 ounce average and a maximum of 8.1. So if I fall between 7.9 and 8.1, I won't get into trouble. And my machine is operating within its normal limits. Okay, so to monitor, okay, which this is our test, okay, we're going to sample 16 packages randomly at random intervals, and we're going to weigh them. Okay, from this sample data, we're going to say that, suppose our test, we have a mean weight of the samples will be used to test the hypothesis that the machine is working correctly. So the data that we're going to draw from this is that it's normally distributed. Again, that's kind of a historical idea. Okay, your population standard deviation is 0.2, and the average of the sample that you pull is 7.89 ounces. Now, if you look at that, you can't just go, oh, well, the minimum was 7.9 and I have an average of 7.89. That doesn't explicitly mean that we have a problem. Okay, it might, but we need to do the test to prove it or disprove it, to accept or to reject, to reject or not reject. as we look at it. All right, so if we use our steps, the first thing we do is we declare step 1. We look for our null hypothesis and our alternate hypothesis. So our null hypothesis is that the population mean is 8. Okay, which means then that the alternate hypothesis would be that the population mean is not 8. Wow, I wrote the 8 sideways. I can't believe I did that. Okay, but that should be an 8 there. Okay, and that our confidence interval on this is going to be 95%, so we're going to choose an alpha of 0.05. Okay, step 2 is we're going to set a random variable x bar as being the average sample weight. Okay, now from previous videos, we know that if it's normally distributed, I can set up a z statistic based off of this shift. Okay, and for a small sample size, or for a sample size of n, okay, I can come in and say, you know, for using basically our central limit theorem, this is basically saying I'm doing x bar minus mu over sigma over square root of n. It's that guy. Okay, and so x bar minus 8 over 0.2 over the square root of 16. Okay, and what will happen is this particular value is our sample statistic for, we'll compute our sample statistic for whatever x bar I try to put in. Now, if you remember from confidence intervals for normal distribution, what we're looking at is a 95% confidence interval had 95% of the area under the bell curve between the two limits. And for a double-tailed region, I had 2.5 at one end and 2.5% at the other. Okay, and for this, we can look up the values, and you know that this is 1.96, and that's minus 1.96. So our rejection region on this, okay, we're going to reject our hypothesis if our sample, or if our statistic for our sample doesn't fall within that range. Okay, so we're going to reject it if it's outside. So first zone is z is greater than positive 1.96, or z is less than minus 1.96. Okay, now, again, because this is symmetric, I can take advantage of absolute value. And so we're going to define our rejection region, which is required for step 2 to be the absolute value of z greater than 1.96. Okay, all right. So let's go through and let's apply our sample data. Okay, so our sample results from the test, we said we took 16 samples. It had an average weight of 7.89 ounces. Watch your units. Okay, and then the population standard deviation was 0.2. Okay, so if I compute my test statistic for this, now, again, we're using a z statistic here, even though n is small, because we know that it's normally distributed. If you didn't know the distribution of this, then you would have to go in and say, well, you know, if it's an n is small, this would probably become a t statistic instead for the population mean. Or if n was greater than 40, or sorry, greater than 30, it would be considered as a large sample. I could use central limit theorem to still use z as my value. Okay, so again, we're choosing z here because we explicitly said that it was normally distributed. So what we do is we calculate the value of the z statistic for my data point. Okay, so that's 7.89 minus 8 all over 0.2 over the square root of 16. Okay, and that's going to be equal to minus 2.20. Okay, and so if we look at our bell curve, and we said that this was 95% on there, and our range was from 1.96 and minus 1.96, we see that our statistic for this value lies outside of that range. We're out in the rejected region. Okay, so that's our step 4. Our decision is that the absolute value of z is greater than 1.96. Okay, it was actually 2.2. Thus, we reject the null hypothesis. Okay, and so now we make a conclusion based off of this, is that we conclude that mu is not equal to 8. And thus, I would recommend that this machine needs to be adjusted based off of that 95% confidence interval. Okay, but let's go a little bit further. What happens if instead we chose to go with an alpha of 0.01, or in this case, a 99% CI? Remember, as you increase the percentage on a CI, the width of this thing gets larger. Okay, so we'll go back through the process, apply it one more time, and we'll see. It's very, very simple, very, very straightforward. So step 1, H naught is still population mean is 8. Alternate hypothesis is mu is not equal to 8. And then alpha is equal to 0.01. That's our 99% confidence interval. Okay, step 2 is we're going to define our rejection region on this. Okay, and so we're going to reject H naught if Z is greater than 2.576. Okay, so again, this is that Z value that came with the 99%. If you don't remember how that comes, go back and look at our normal distribution video. We spent some time talking about those values, but you can find that for the area, the Z values that correspond to 99% inside of there will be for points at plus 2.576 and minus 2.576. Okay, now our sample statistic is unchanged, it's still 2.2, but now you can see that by moving this thing out, now my minus 2.2 is located inside that range. Okay, and so, you know, for us, our Z statistic is less than 2.576, hence we fail to reject H naught, okay, or that mu is equal to 8 ounces. Okay, we can't say that it isn't, that it's not working normally. Okay, so our conclusion then is that we do not recommend adjusting the machine. Now, here's the dilemma in this, is that we failed to reject H naught. This does not imply that H naught was accepted. H naught, this machine may still be malfunctioning, but we don't have the data on this test to be able to say that, you know, without a doubt that we have accepted it, or that we, you know, or that we failed to reject. That's the kind of the outcome that's in this. So it is possible this machine still needs maintenance, but, you know, generally in a controlled environment, you know, such as quality control, they're constantly testing, and so they would say, well, let's go do another batch of tests and see where we fall on that one as kind of a follow-up. But, you know, if we had come in and found that this value was -3 or something crazy down there, then at this point you might go, yeah, we're well outside of that range, we should probably test this thing, okay, or make a modification to our equipment. So anyway, I know it's kind of a shorter video, and I hope this kind of gives you kind of a sense of what you can do with hypothesis testing. Okay, we've done kind of a simple one. This is just for a sample mean, but you can do, you know, population tests for proportions. You saw that when we were playing with the alphas and the betas. You can do it for, you know, for variances, and there's a whole lot of different ones of these that, you know, we'll cover in future videos. But for now, I'm just kind of trying to introduce the concept of how we can start to formalize our procedure for conducting a statistical test. Okay, so it's all about the null hypothesis and the alternate hypothesis, and then what level of confidence are you wanting to make a decision about. Okay, and there's some pretty good power on this stuff. You know, you can do some pretty powerful things once you get the hang of setting up these tests. Now, this is the basics to how you would set up a quality control program. You know, a certain amount of maintenance, you can start tying other data values to that, and so on and so forth. So anyway, like I say, I hope it made sense to you. As always, if you'll leave comments down below, if you got any questions, we can make some follow-up videos to kind of to carry on this if you guys feel like you need it. Otherwise, please be sure to like the video, and as always, make sure you subscribe to our channel. It will help us out. So anyway, hope you all have a wonderful evening, and we will see you guys next time. Happy engineering.